Muted.
Good morning, everyone. Welcome to today's webinar on the NASA Tournament Lab In-Situ Materials Challenge. My name is Jonathan Yakasha from NineSigma, and I will be your host and moderator for today's webinar. Please note that today's webinar is being recorded and will be transcribed for viewing on the NASA Hub on 9 sites at a later date. We'll begin by going through the agenda for today's webinar. First, I'll provide the speaker introductions and a brief overview of the challenge. Next, our speakers will share with us NASA's interest in open innovation and the details of the challenge. Then we'll present the frequently asked questions for this challenge. And finally, we'll work through a live question and answer session. If you have any questions for our panelists today, please use the Q&A chat box to submit your questions at any time. Today's webinar is an excellent opportunity for you to pose your questions directly to both the NineSigma and NASA teams. We will collect and present these questions during the live Q&A section. If we're unable to answer your question during today's webinar, we'll be transcribing and answering all of the questions asked during the session and posting them on the contest forum on 9 sites for viewing at a later date. And to close out today's webinar, we'll wrap up with information on what you can do today for the NASA Tournament Lab In-Situ Materials Challenge, including where to register, connected, and how to submit your proposal. Now I'm pleased to welcome the following speakers to our webinar this morning. From NASA, we have Steve Rader, Deputy Manager, Center of Excellence for Collaborative Innovation at Johnson Space Center. And then from the Kennedy Space Center, we have Jack Fox, Tracy Gill, and Rob Mueller. Jack is the Chief of Science and Technology Project Division. Tracy Gill is a Technology Strategy Manager. And Rob Mueller is a Senior Technologist. And from NineSigma, we're happy to have Kevin Andrews, PhD, Senior Program Manager. And now the overview of today's topic. NASA is seeking proposals for systems that will convert in-situ materials into interlocking structural elements for construction that can support exploration on a planet. NASA is seeking materials that can be converted into interconnecting materials for launch pads, blast protection berms, roadways and walkways, equipment shelters, pressure vessels for fluid storage, ablative atmospheric entry heat shields, construction foundations, and other structures. And now Steve will tell us about NASA's Center of Excellence for Collaborative Innovation and the Tournament Lab. Steve?
Thank you, Jonathan. My name is Steve Rader, and I'm with the Center of Excellence for Collaborative Innovation at NASA, and we actually work across all of NASA and the federal government to promote crowdsourcing and challenges, and we're very excited about all the challenges that we are able to put out to the public. Next chart. We actually provide the NASA Tournament Lab, which is what our main brand is that we have out there, and this includes challenges that we run across NASA, and we have just recently started a contract with NineSigma, and so we're happy that this is one of 2 challenges that we've recently launched with NineSigma, and we're very excited about what this challenge will bring. If you're interested in participating in other NASA challenges, we have lots of them. We have them under Centennial Challenges. We also have the under NASA COSI, the website you see there, nasa.gov/solve, and challenge.gov are all places that we post our challenges. Each one of those has all of our challenges. And so if you're interested in participating with NASA and really helping us to solve some really hard problems, we encourage you to log on and actually help us out. So we're looking forward to what we get out of this. And back to you, Jonathan.
Great. Thank you, Steve, for that introduction. And now Tracy Gill will present an overview of the in-situ resource utilization. Tracy?
Thanks, Jonathan. So we represent the KSC SwampWorks Labs. We're really about finding rapid, innovative, and cost-effective exploration mission solutions. We like to do partnering across NASA, industry, and academia, and we believe space resources are critical to the sustainable exploration approach. So what are we talking about when we say space resources? Well, we have kind of 5 groupings that we've included here. There's traditional resources, which are the water, atmospheric constituents, volatiles, and things you find where you go. There's non-indigenous resources. Those are the things you bring with you that maybe you don't think about. It's your waste, it's the extra hardware that you don't use, and your sturdy air, all kinds of things like that. And then energy. So there's sunlight, and then there's permanent darkness, and you could take advantage of both of those. There's environment. There's vacuum, there's microgravity or reduced gravity, and then high thermal gradients. You can take advantage of that as well. And then finally, location. Your location is useful too. You can have Earth viewing locations, sun viewing, space viewing, and then staging locations, which are advantageous spaces in the out in space where you might stage hardware. And then we've included a little picture that it kind of shows some of our a nice sculpture that shows some of our philosophy. You have a suited astronaut there with a robot arm, and he's using a mining robot to help him build pavers and lay out a structure there. And that sculpture happens to be made out of Regolith simulant, and it's outside of the SwampWorks labs today. Next chart. So when we talk about ISRU, it's kind of evolutionary there. You got to walk before you can run. And when you start on the left there, you have kind of your low-hanging fruit, the easiest things to do, or maybe getting propellant and oxygen and fuel. Then as you evolve to the right, it gets a little bit more complex. You can get the commodities for fuel cells, and you can start to do some basic manufacturing. And then way over there on the right, you have advanced space manufacturing, space solar power, and lunar and asteroid mining for resources there. Now, why are we doing this? Well, we're trying to harness and utilize resources and create products that will help us do the exploration mission by reducing mass, cost, and risk. Next chart. So this is kind of a silly chart, but we wanted to show it anyway. It kind of brings the message home. If the wagon pioneers had tried to take the model of you can only use the things you bring with you, they'd have only gotten about 100 miles. That's not a very smart plan, so we don't want to use that plan. So we're going to take advantage of resources, and that's why we want to do ISRU. Next chart. So what are the things ISRU can do for you? Well, obviously there's launch mass savings. You can carry less. You have to bring less stuff. Less propellant, less life support, etc. And then when you do that, you can reduce your launch numbers, and that obviously increases your chances of mission success. You can extend the life of your missions because you can take advantage of the consumables at the site rather than bringing them all from Earth. And then it also allows you to repurpose hardware that's at the end of its life once it's run out of its resources. You can improve crew safety by having dissimilar redundancy. You have more margin with your consumables. You have extra radiation shielding, and then you increase your independence from the Earth. You can provide critical solutions for mission assurance. That includes having safe landing zones and having extra propellant for return to Earth. You can relax critical requirements, meaning your propulsion has to be less efficient. You don't need as much closure in your life support system because you can rely on the things you find there. And then you may be able to enable mission capabilities that were not possible without or difficult without ISRU. You can reuse landers and space transportation. You can have surface hoppers. You can have extra equipment for surface mobility. And you can extend the duration of your activities in extreme environments because you've got these new capabilities. Another element is you're enhancing crew psychological health. They know that they can rely on themselves and they're not as dependent on the logistics train back from Earth. And then the other thing it's doing for you is it's enabling space commercialization opportunities. You develop those technologies, then there's opportunities to commercialize them and reduce life cycle costs because you have commercial providers doing that service for you. Next chart. And then most of this text you've seen before. It's we're really looking for those in-situ materials that are being converted into structural elements for construction that can support exploration on a planet. So you either have to bring everything you need with you, or you have to take advantage of what you find, and we want to take advantage of what you find. And then we want to create structural elements, and we just gave you some examples. There's launch and landing pads, There's berms that protect you from the regolith dispersion. There's roads and walkways. There's micrometeorite thermal and radiation shielding. There's shelters. There's pressure vessels. There's heat shields, foundations, and tons of other examples I'm sure you can think of that we may not have thought of so far. And then really we're looking for solutions for these the construction into useful structural elements or even partial solutions. And then lastly, we've created, we added a picture there to kind of show some of the things we're working on in this vein. We have our robot we called Razor. It's the Regolith Advanced Surface Systems Operation Robot. It's a lightweight mining excavator for operating in reduced gravity, and it's one of the things we think might be useful, this kind of architecture, and we thought it might, including it might give some folks some thought as well. That's all we have, and back to you, Jonathan.
Great, thank you, Tracy. Kevin, could you please share with us the criteria for this challenge?
Absolutely. So the idea is to maximize the use of regolith to produce those useful building blocks that support planetary construction. And if you look at the request challenge summary, we talk about some calculations that you'll need to do in preparing your proposal. So obviously, we'd like to have higher values of capital M and capital R. We'd like your solution to be compact enough to fit payload package constraints, which are listed in Table 2 of that summary. We're looking for systems that will be designed for ease of assembly, operation, and maintenance, that will use energy efficiently. So calculated efficiency factors that are larger are generally better. Your possible approaches might include, but are not limited to, metals extraction, polymer synthesis, block shape extrusion, material sintering. Keep in mind that just because you can suggest a high value of M&R, that doesn't guarantee that you would necessarily fall to the top of the list. There are other considerations, such as the quality or utility of the material produced. So in terms of the In-Situ Materials Challenge timeline, this project was launched on October 7th. The deadline is December 3rd. We are here today at the webinar on the 10th of November, and we plan to announce the winners of the challenge in late January 2016. Please be advised that the response deadline on December 3rd is 5 p.m. Eastern Time, U.S.
Great, thank you, Kevin. Before we proceed to why solution providers, such as our attendees today, should be interested in this project, I would like to reiterate that if you have any questions for our panelists, either for Kevin or our attendees from NASA, please use the Q&A chat box to submit your question at any time. Thank you. So, Kevin, why should people be interested in this contest?
Well, it's an opportunity to win a prize. The top winner is going to receive $10,000. And there will be 2 second-place winners that each receive $2,500. What else? Well, there's recognition of prize winners by NASA. You will be in published announcements. There will be individual profile stories. There may even be an opportunity to visit the Kennedy Space Center, albeit travel expenses will not be included as part of that.
Okay, great. Thank you, Kevin. Now we'll proceed to the challenge frequently asked questions. These are questions that are often asked about NineSigma projects in general, or have already been submitted at the forum or to the provider help desk. Kevin, what can you tell me about intellectual property? How am I protected?
So keep in mind that respondents need to submit non-confidential information. The acceptance of a prize will grant NASA an unlimited royalty-free license to use the winning methodologies. Also, there are additional concepts conveyed in the terms and conditions document. We advise you to review that document carefully.
Okay. What's the best way to respond?
So the best way to respond is to register and complete the online proposal template. Keep in mind that posts on the forum are not eligible responses.
Okay. Now, what if I only have a partial solution?
NASA has told us that they're absolutely interested in those innovations and approaches, even if they can only address part of the challenge.
Okay. If you would, Kevin, could you please explain NineSigma's role in this contest?
Sure. NineSigma has been contracted by the NASA Tournament Lab to run this challenge and to solicit responses. NASA will receive every eligible entry and will solely determine the winners.
Okay. Is there an opportunity for follow-on work beyond the contest?
Open innovation at NASA is intended to help NASA identify and connect with new innovators. Additional follow-on work is possible, but it would be subject to regular government procurement procedures.
Okay. And one last frequently asked question, what if I don't really have a complete solution, just a really cool idea that I think would help NASA?
Well, all eligible submissions received by NineSigma will be submitted to NASA. However, you maximize your chance of winning by being attentive to the evaluation criteria stated in the challenge summary.
Okay, all right, thank you. At this time, we'll open up the session to any questions from the audience. Please continue to submit your questions through the question and answer chat box. We'll take the rest of our time today to answer them live. Remember though, if we're unable to get to your question today, our question and answer session will be archived and made available on the contest page following this webinar.
Okay, so we have a question from the audience. How do we access the proposal template? When you're viewing the challenge website, there is a button, a blue button labeled Respond. Click that button and the template should appear. There will be some questions that you can answer, and there's also an opportunity to upload supplemental documents. All right, so our next question.
I think would be most beneficial to be addressed to the NASA team. Regarding payload constraints, should we assume that current descent technology limiting total payload mass, or can we reasonably extrapolate to include our payload as part of a larger package that is likely already part of a NASA Mars mission?
Okay, good morning. This is Rob Mueller at NASA Kennedy Space Center. So the way I understood that question is it's the mass available for the entry, descent, and landing system on Mars. Is that correct?
That appears to be the intent of the question, yes.
Okay, so currently, if you look at the missions we have today, the current landing systems for the Mars Science Lab, which was the JPL Sky Crane, was able to land about 1,000 kilograms of useful payload on the surface of Mars. And that's at the lower altitudes in an equatorial region. So with today's technology, we are constrained to 1,000 kilogram payload. In the future, the NASA missions plan to have landers that can do as much as 18,000 kilograms, 18 metric tons, and possibly 27 metric tons in that range. So at that point, it becomes more feasible to do higher payloads than today's capability. However, that should not matter for this competition because in Table 2 of the rules, we describe the payload mass of 700 kilograms. So this is transportation agnostic. You should just assume that NASA will find a way to get this payload to Mars, and all you have to do is stay within the constraints of Table 2.
Great, thank you.
The next question. Can we assume the availability of water, as recent finds suggest this is readily available?
This is Rob Mueller again, and water has been found on Mars by the Phoenix mission, but the Phoenix mission landed at a high latitude. The recent Mars landing workshop that was held in Houston 2 weeks ago address these issues, and there's a whole website dedicated to that. And we're currently asking the architectures to stay within plus or minus 50 degrees of latitude on Mars for orbital mechanics reasons. And so that means that the polar ice is not really available to the mission. However, Mars is in a state of glacial retreat, so between 40 and 50 degrees latitude, there is possibility of receding glaciers that are fairly accessible within 1 meter of the depth of the regolith. And so you could excavate water ice potentially at the higher latitudes between 30 and 50 degrees. At the lower latitudes, you can extract water from hydrated minerals, is what we suspect. That's what the orbital data is showing. And some of the data from the Curiosity mission also shows there are hydrated minerals. So there is water available on Mars. Whether you assume if it's accessible or not, you could assume it's accessible within 5 to 8% of water yield, and then that would dictate how much regolith you have to actually excavate.
Great, thanks, Rob. I'd just like to reiterate, if you have any questions for either Kevin from the NineSigma side or any of the gentlemen joining us from NASA, now will be an excellent opportunity for you to pose your questions to one or both of those teams. We've got a number of questions coming in, so that's great to see. Please take advantage of this opportunity. Our next question is again for the NASA team. Does the solution have to be individual building blocks? For example, if I can make fibers and a matrix from regolith, do I have to make interlocking blocks with that material, or can I make an entire pressure vessel directly?
This is Rob Mueller. The intent of the challenge was to create structures. And the reason why the challenge asks for modular building blocks is because you can now use those modular elements to make more than one structure. If you make a pressure vessel out of basalt fibers that are extruded and then made into a composite material of some type, that's a great solution, but it limits you to just one application. What we're seeking is a modular system that can be reapplied into many structures. So think of it as a kit, a building block kit, and almost like a Lego kit or Meccano kit, something like that, that is modular, that can be made into many different configurations, because that's what pioneering requires. Think of a log cabin. When the pioneers went out west, they had many ways of building log cabins using these logs. So it's a modular building method is what we're looking for.
Great, thanks, Rob. This next group of questions will be directed at Kevin Andrews from NineSigma. Kevin, can we form teams of 2 friends, for example?
Absolutely. Submitters may be teams. So submit your proposal. You know, one of you would submit the proposal and indicate who else on your team, you know, what other, how you're associated.
Okay. Next question for you, Kevin. Are are non-U.S. teams eligible to participate and to win the prize money?
As long as you meet the terms and conditions, I believe the answer is yes. As long as you are from a location that that the United States government recognizes as someone they can do business with.
Great, thank you, Kevin. One more question for you. How should we provide video? A link to YouTube?
Yeah, that would work because videos tend to be rather large. But maybe NASA has some insight.
Do you, NASA team, do you have any restrictions as far as video presentations? Steve?
Yeah, I don't think we do. I think, you know, there's the hosting thing that you guys talked about, but unless, Jack, you guys have any reasons that that would just augment and help us. Obviously, the length should be reasonable. You know, adding a 2-hour feature might not be something we want everyone to do, because just from a time-consuming standpoint. But if there's aspects of your proposal that you think would be enhanced with a video presentation, and it's reasonably packaged, I think that's probably okay. Let me just, Jack and Tracy, you guys good with that?
Yeah, this is Tracy Gill at KSC. Yeah, Jack and I and Rob are all looking at each other, and that seems like a reasonable thing. I agree with you. We don't want a 2-hour movie, but maybe a short video that helps illustrate what they're trying to propose. If that's done in a reasonable manner, it might help us understand what the proposal is. So no problem with that.
Great, thanks guys. Our next question would go to the NASA team. To what degree must structural elements be interlocking?
The structural elements need to be interlocking in order to give structural integrity. If there's any kind of disturbance in the environment, think of even the moon still has moonquakes today. If you had any kind of load go on that structure, side load, it needs to be interlocking. Needs to have structural integrity. So one of the rules states, let me try to find it here, rule number 6 in the requirements, under requirements number 6 says, if your approach creates structural elements, assess the strength of the elements, compression, tension, and bending, accounting for material formation and assembly technique by analysis or test, and describing test methodology. If your structural elements are not interlocking, then compression, tension, and bending will not be very good. So if you think of a pile of bricks that are assembled today without mortar, those bricks will not have much structural integrity. Well, what we're looking for is a solution that has interlocking structural elements where you don't need a mortar or cement, and you still have structural integrity. So that's up to you. You need to find a solution where you have the highest possible compression, tension, and bending with the solution that you have using an interlocking structure. And that's the challenge.
Okay, Rob, thank you. We've got a follow-up question here that would probably be best addressed by you. Are the structures to be built intended to be built by humans or robots?
This is Rob Mueller at NASA Kennedy. The structures ideally would be capable of being built by robots, helped by humans. We call that cooperative robotics. So it would be a robot working side by side with a human. However, it would also be NASA's plan to send robotic precursor missions to the destination, and the robots would prepare the site for the humans. And so if you go to a construction site on Earth today, there's many yellow machines there. It's not like in the days of building the pyramids where we have thousands of people doing the manual labor. It's a human crew augmented by robotic capabilities. So we need a robotic assembly capability, and the humans would supervise that. So probably the answer to your question is yes, we need to have a robotic assembly capability, but there can be an element of human supervision.
Okay, thanks. Our next question, do we need to make interlocking building blocks, or is it sufficient just to create arbitrary strong structures by any means?
Well, that's an interesting question. I would encourage you to read the rules, and there's a sliding scale formula, and you should try to win the competition under the constraints of the rules that we have published. And there's a wide variety of solutions possible, which will be scored according to the formula. If you have a better way of doing it than interlocking favors, we certainly want to hear about it. And so we're not trying to limit creativity, but the baseline is interlocking structures. If you have a better solution, then please let us know about it and we'll score it, and it will rank against all the other entries. But so I would say if you have a better solution, please propose it.
Okay. Another follow-up question to that last one: do the building blocks need to be seamless, and their unions with other building blocks too?
No, in space we're looking for structures, but the integrity of the structure against vacuum would probably be handled by an inflatable bladder or a seal on the inside of the structure. So that's a separate problem. We're not asking the structure to be airtight. That's a separate problem. But on that note, many people on Earth, when they look at structures, that because of the gravity on Earth and the atmospheric pressure, we typically think of structures as being in compression. In space, a lot of these structures will be in tension. If it's a pressurized structure, that structure will be in tension. So that needs to be something that is considered in the design of the structure. If it's an unpressurized structure, for example, a hangar for storing equipment, or a wall that is never subjected to any kind of pressure, then it's okay to work under compression. But if you're working in a pressurized environment inside the structure, then you have to account for the tension applied by that pressure, unless you make a structure that's just a shelter and you have an inflatable bladder inside that shelter which confines the pressure. So there's many solutions, but we're not asking for these structures to be seamless, and we're not asking for these structures to be airtight. We're just asking for structures that have capability to carry loads.
Great, thank you. Just want to remind everybody that we've got a lot of good questions coming in. Hopefully we will be able to get to all of them today. If we are not able to get to all of them during today's webinar, the questions that we don't get to will be transcribed and posted on the contest forum at a later date. Our next question: should the building blocks be made on Earth or on Mars?
So let me ask you this question. Would you launch concrete into space? The whole point of this challenge is to avoid launching mass into space, so we definitely would not make them on Earth. The only reason we would make them on Earth would be to test them on Earth, make sure they work. The whole idea of this challenge is not to make things on Earth, but to make them in space. So what we need a design and a method and a payload. We send that into space, and then there's a massive multiplier effect on that payload, because the payload is able to create a useful mass that is many, many times its own mass. So we absolutely want these modular building elements to be made in space using local materials. We would never think of launching such a heavy mass into space when we have local resources that we can use at our destination.
Great, thank you for that explanation. Our next question: should human habitability be considered in your proposal?
No, it's not a requirement to consider human habitability. It is a consideration, but not a requirement. And it goes back to the previous question on whether it needs to be airtight or not. Right now, we're just asking for a structural capability, and that structural capability has many applications. It could be used for a habitat, for human habitation, but that's not the only use. So think of it as building infrastructure. And if you go to Antarctica and set up a base in Antarctica, you need certain things. You need a runway, you need a land, then you need roads, you need to be able to transport what you land, then you need shelters for your equipment, and then finally you will need shelter for humans, which will have a certain configuration. but that's just one of the applications of this system. So you should not constrain it just to human habitation.
Okay, great, thank you. With respect to the high values of M and R, could you please provide target ranges? Is there a minimum threshold?
Well, really that's for the competitor to decide. I don't think we're going to give out examples of M and R. That depends on your design. So you have the formula, and your goal, your task is the challenge is to maximize the points you can earn with that formula. So that's up to you.
Okay. Our next question, can you please provide any guidelines for an estimation of mean time before failure of equipment?
All our equipment is designed, when you go to Mars, in a certain architecture, which NASA is considering now, you have a 6-month journey to Mars, and then you're committed to staying on Mars for 1.5 years before you return. And that's another 6-month journey. So it's a 2.5-year round trip for every Mars mission. However, if you want to pre-and place equipment on the surface of Mars, you have to do it at a prior launch opportunity. There's only one launch opportunity every 26 months going to Mars. So at a minimum, you have to be capable, this equipment has to be capable of lasting for 2 Mars opportunity cycles, which is about 4 years. So that would be the very minimum we'd want this equipment to last. And we usually design our equipment to last about 5 years. However, if you think of space station in low Earth orbit, it's been there 15 years already, and they plan to use it out till about 2024. So a more realistic and desirable timeline would be for this equipment to last 10 to 20 years. However, 5 years would be the minimum threshold, and the goal would be to last about 10 to 20 years.
Okay. These next 2 questions that have come in are related, so I'll phrase them together. Even though power harvesting and storage are accounted for, what sort of power constraints can be expected for the Regolith processing system? Is there a minimum kilowatt available?
That's a good question. It depends on what your power plant is that you bring. In the early stages of the missions, the precursor missions, there will be no power plant available, and so you'll be under 1 kilowatt, and it will be just from solar panels. In the later missions, we'll have a 50 kilowatt power plant available, and for example, the ISRU propellant production plant that we plan on using today consumes about between 25 and 30 kilowatts. So it is possible that you'll have a very good power source once we get the power plants deployed. And so just assume that you'll have enough energy, because 50 kilowatts is a lot of power. And so just this challenge does not, under rule number 2 of the requirements, it states you do not need to include lander mass or energy sources. So that's not part of the challenge. Just assume that you do have enough energy to do what you need to do, which will most likely be under 50 kilowatts.
Okay, great, thank you. Before we proceed to our next question, just like to reiterate one more time that this is an excellent opportunity for our attendees to ask questions directly to the NASA team and get an immediate answer. And if they're not able to answer it now, an answer in a few days. We also have an excellent resource here in Kevin Andrews from the NineSigma side, who's more than ready to answer any process questions that you might have in terms of responding to this project. Moving on to our next question. Is there already a system for separating the regolith into the substances listed on Table 1?
I'm just looking at Table 1 here, and I assume you're looking at the oxides on the left-hand column. as you go to the right, it shows the different simulants we have at the different destinations. So you have Moon, Mars, and Earth. All of those oxides that are listed there are in the mineralogy. So these are oxides, these are compounds, they're naturally occurring compounds in the minerals, and they're bound, they're chemically bound. So there would have to be a way of extracting those oxides, and so that is not accounted for. But maybe Jack, you want to talk about one of the references?
We're saying use this powdery basalt, and in the assumptions it's got, you don't need to provide a robotic excavator that delivers the powdery basalt to your device. But like Rob said, if you're planning on extracting anything out of the basalt, that would be part of your device.
Yeah, the raw material is basalt. If you plan to use iron or magnesium and you have to extract that from the regolith, then that counts against your payload mass. But the excavation of the regolith does not.
Okay, great. We're going to turn now for a question to Kevin Andrews. Is there a community forum to find groups in order to work with?
So there is a forum for this topic and for the other NASA topics on our Nine Sites NASA Hub. At the moment, we do not have a thread regarding finding partners, but we can certainly create one. So we'll do that after the webinar.
Okay, great. Thank you, Kevin. Turning back to the NASA team, can we specify specific landing sites within the lab to gain access to specific materials as observed by orbital probes?
Yes, in fact, we just had a workshop that's online. It should be publicly available soon, where we discussed all the landing sites on Mars and what the resources are that are available at those landing sites. So I don't think in this challenge we ever specified or asked you to specify a landing site, but it would inform the kind of resources that are available at that landing site, so it would be useful, but it's not a requirement to specify a landing site.
Okay. Our next question. What if I have an idea for utilization of other materials, for example, atmospheric CO2? Would this be eligible for this contest?
Go ahead.
Yeah, I think we addressed this one in one of the earlier questions we got offline. You can take advantage of any constituents you find. It's not just a regolith. Atmospheric constituents are available as well.
Excellent. Thank you. Our next question. If we can't experimentally test our materials processing method due to limited time, what level of analysis and simulation is considered enough to meet the requirements?
I'd like to refer you to the NASA Technology Readiness Level scale, which is available online. And if you just search on NASA Technology Readiness Level, TRL, there's a scale. And the scale shows all the different levels of development. And if you don't get to TRL 6, which is testing in a relevant environment, then you should specify the level of TRL that you're at. And for example, if you do a bench test of, if you make one modular structural element in the lab using relevant materials, that's TRL 3 or 4. If you're in a vacuum environment or in the field, then that would be more like TRL 5 or 6. So as long as you specify what TRL, technology readiness level, that you're at, then NASA can assess it based on that TRL. So doing it in the lab is not a prohibitive thing, but we would like to understand what level of TRL you're at.
Okay, great. We've got another really good question here. Will solutions for Mars have a higher weight in the competition than solutions for the Moon?
No, I think we're going to go by the, we have some scoring there with the M&R, and we're going to try to be destination agnostic, which is one of the reasons we provided the table with samples with basalt on the Earth as well as the regolith on the Moon and Mars. So we're trying to be destination non-specific. So I don't think that we would score more favorably one way or the other. We're going to evaluate the quality of the solution, and we hope that the solution might be applicable in several destinations.
Okay, great. Our next question, can you tell us what technologies are required to enable in-situ resource utilization? Perhaps this one would be for Tracy.
I'm sorry, we just didn't hear the question, but I think you said what are the technologies that are required to enable ISRU?
That's correct.
Okay, we'll need advanced robotics to acquire regoliths. We'll need chemical processing plants to extract resources from the regolith, automated manufacturing methods to make parts and assemblies. And so the main purpose for these technologies is just to make space exploration sustainable in the long run. By reducing and eventually eliminating the transportation of supplies from Earth to the destination, we can achieve this. So the whole point is to live off the land in space. There's many, many resources in space. We just have to learn how to use them.
Excellent. I'd just like to remind all of our attendees and panelists, we're approaching the end of our webinar time today. If you have any additional questions for either Kevin Andrews on the NineSigma side or any of our NASA panelists, now would be a great opportunity for you to ask them. Our next question is, why is modularity so desirable?
Modularity is desirable because it's efficient. When you have a modular system that can be reconfigured into many solutions, it's a very efficient solution. It's mass efficient, it's energy efficient, it's versatile, and it's flexible. So it's also a very reliable system and robust system. If something goes wrong, the astronauts can reconfigure a system into a new solution. So modularity is just desired because it's versatile and efficient.
Excellent, thank you. Our next question, what should be the main differences between these new building blocks and the blocks that we already use here on Earth?
We don't know of any blocks used here on Earth that don't require a mortar or cement or rebar or some of these conventional technologies on Earth. Typically on Earth use Portland cement, and we don't anticipate having Portland cement in space made locally. It is possible, but it's very energy intensive, and the materials required are not common on Mars or on the Moon. So we really would like a solution that is new and different. It has to have structural integrity is the main criteria. It has to be able to be made locally by a payload with the mass constraints given in the rules, which is 700 kilogram and inside a payload volume of 2 meter cubed. So that's a challenge. You have to create a device that can use local resources, the regolith or any other resources you find, and make a useful building block out of it. Today on Earth, we just have bricks, and there are not many modular building elements on Earth that are made out of local resources. And so that's the challenge. If something does exist on Earth that can be repurposed, then that can be submitted in the challenge.
Okay, great. Our next question will turn to Kevin Andrews from NineSigma. Can I work with other people even though we're far away from each other, i.e. in different countries?
Absolutely. I mean, it's perfectly fine to collaborate across the globe as long as the parties in each location are able to interact with NASA according to the terms and conditions. That's fine.
Okay, great. Thank you, Kevin. We have another question for the NASA team. Could you please explain what basalt is and why it's such a desirable material?
Basalt is a rock, and it's a rock that is made up of minerals, and the minerals have a volcanic origin. So it comes from lava, essentially, and there's various kinds of basalt on Earth and in space, but basalt is one of the basic building blocks of the solar system. Almost every planet or moon or many asteroids have basalt available, so it's just a very common material on Earth and in space. It's also on the moon and Mars. It exists in a granular form. It's been actually impacted by meteorites, so what it ends up being is crushed rock. So basalt is a rock and regolith is crushed rock, and there is a lot of crushed rock available in outer space. If we can use that crushed rock as an aggregate in a concrete system, then we have saved a lot of launch mass. So the reason we're interested in basalt is because it's commonly available. It's a very hard rock, so it has good structural properties. And if we can use this commonly available granular material as an aggregate in a space-formed concrete, then we'll have tremendous mass savings. We'll save thousands of tons that are launched, would normally have to be launched into space. That's why we're interested in basalt.
Okay. We have just a few more minutes here. We've got another question we'd like to pose to the NASA team. Is it possible to melt the regolith and shape it into our block?
Yeah, absolutely. It would just be factored into your mass calculations. What type of equipment did you need and what energy did you need to accomplish that?
Okay, great. We have just a few more minutes, as I said. If you have any last-minute questions for the NASA team, please avail yourself of this opportunity right now to submit your questions. If we don't have time to get them answered live during today's webinar, we'll post the questions in the forum and get you an answer that way. At this time, we'll move on to what you can do today. First off, you can visit the contest site. You can see the URL there. It's ninesites.nine-sigma.com/web/nasa-in-situ-materials. While you're there, you can register to respond to this project. You can view the frequently asked questions, and you can subscribe to the contest forum. If you need any help with your registration or you have a question as far as what you need to do next, there's two ways to contact the provider help desk. You can contact the provider help desk at the number on your screen. You can also use the email listed there. It's phd@ninesigma.com, and we'll do our best to get you the answer as quickly as possible. Also, please keep in mind that the submission deadline is December 3rd, 2015 at 5 p.m. Eastern Time in the U.S. If you attempt to respond after that 5 p.m. deadline, I'm afraid you'll be out of luck. So please keep that in mind when you're preparing your proposals.
I also want to remind you that at the NASA Project Hub on 9Sites, there's another project regarding EVA spacesuit materials. So we encourage you to take a look at both projects.
Great. Thank you, Kevin, for that reminder.
And if I can jump in, sorry.
Sure.
This is Steve Rader. In addition to that, since this is regolith-based, we do have another regolith challenge that is the Centennial Challenge for 3D printed habitats that I encourage this community in particular that's interested in working with regolith to check out at nasa.gov. Just search for 3D printed habitat challenge. You should be able to find that.
Great. Another interesting project for our solution providers to consider. We've got a couple of questions that have just come in. I'm afraid we won't be able to get to them during today's webinar, but as I said, we will get answers for you and post them to the forum. We'll go ahead and we'll leave the presentation open, the webinar open for just a little while longer here to get any last-minute questions that you may have. But we're going to go ahead and close out today's webinar. We'd like to once again remind everyone that the contest deadline is December 3rd of this year at 5 p.m. Eastern Time in the U.S. Thank you very much for your time. Thank you very much to all of our panelists for attending. Thanks, and have a great day.